adjacency matrix representation and another is adjacency list representation. For example, in this particular slide, you can see that there is a graph which consists of, it is in fact a weighted graph, weighted undirected graph. It have 7 vertices and number of edges. So the adjacency matrix will be a 7 cross 7 matrix which will represent the vertices. So if there is a path from one vertex to another vertex, then the weight of that path is represented. Otherwise, there is no path, then it is represented by infinite value. For example, in this we can see that from A to B there is a path which have weight 2. So in the matrix A to B or B to A, in case if it is undirected graph, so A to B and B to A both are same. So A to B is having value 2 in the matrix, or B to A is having value 2. Similarly, from A to C or C to A there is a path having weight 1. So in the adjacency matrix, in the first row, say A to C, the entry is 1. But there is no path from A to direct path from A to D, A to E, A to F or A to Z. So that's why infinite value is represented in those cells in the adjacency matrix. And in this way we represent the entire graph using the adjacency matrix. Similar way it is used adjacency list also, in which there is a linked list maintained for each of the node. A separate linked list is maintained which represents the nodes or vertices which are reachable from that particular vertex. So as today's topic is to discuss minimum cost spanning tree. So before we discuss minimum cost spanning tree, let me introduce what is a spanning tree. So spanning tree is a tree which is a subset of graph such that all the vertices are connected using minimum possible number of edges. What is the meaning of that? It is connected with the minimum number of possible edges. So for example, if there is a connected graph having v number of vertices, then number of edges in the spanning tree for that graph should be 1 less than that of the vertices. For example, if we have a graph having 5 vertices, then the spanning tree should contain only 4 edges. And a spanning tree does not exist for a disconnected graph. This is one of the important. It is only exist for spanning tree can be created only for connected graph. If there is a graph whose vertices are not connected, then we cannot create a spanning tree for that graph. And because spanning tree is a tree, so as we know that tree should not have cycle, and also a graph may have more than one possible spanning tree depending on what combination of edges we consider for creating the spanning tree. Or in general, if we consider a complete graph means each vertex in the graph is connected to every other vertex with say v number of vertices, then in that case there will be v to power v minus 2 number of spanning tree. For example, if there is a graph, complete graph having 4 vertices, so the total number of possible spanning tree will be 4 to power 4 minus 2, that is 4 to power 2 or 16. So here in this slide you can see that there is a graph having 4 vertices. It is a fully connected graph. So for this, the spanning trees, possible spanning trees are given below that graph. So we can see that for 4 vertices, and if it is fully connected, then there are 16 possible spanning trees. So all 16 possible spanning trees are shown in this particular graph, and we can see that every spanning tree is having 4 vertices and 4 minus 1, that is 3 number of edges. So that is the definition of a spanning tree. But now comes what is minimum cost spanning tree, because today's topic is to discuss the minimum cost spanning tree or minimum spanning tree. So a minimum spanning tree is basically a spanning tree that has the minimum weight among all the possible spanning trees. So as I told that there may be more than one spanning tree possible for a graph, then out of those spanning trees, which one is having minimum sum of weights? So that is known as minimum spanning tree. So properties, if we discuss what is the properties of a minimum spanning tree, then it should have first of all the properties of a spanning tree, that it should have mod of v minus 1 number of edges, that is number of vertices less than 1 edges should be there. And because it is a tree, minimum spanning tree is also a tree, so it does not have a cycle, because if there is a cycle, then that is not called tree, it becomes graph. And MST may not be unique for a graph. There may be sometimes more than one minimum spanning tree possible for a given weighted graph. And selected edges. So today we are going to discuss the Prim's algorithm basically to create the minimum spanning tree. So selected edges in Prim's algorithm always form a single tree. So here in this slide you can see that the upper one is the graph and the bottom one is the minimum spanning tree. Now the question is how we can create minimum spanning tree with the help of Prim's algorithm. There are many algorithms to create minimum spanning tree. For example, Prim's algorithm is one, Kruskal algorithm is another one, but today we are going to discuss the Prim's algorithm. So let us first discuss how this Prim's algorithm works for creating the minimum spanning tree. So in the Prim's algorithm, there are 4 inputs. For a given graph, there are 4 inputs which are available, using which we can create the minimum spanning tree. What are those 4 inputs of the graph? The first is the set of vertices, that is V. Another is the set of edges, E. And for each edges, the weights are assigned. So that is represented by W. And also another input is the root. Root means source node from where we want to start to create the spanning tree. So in the Prim's algorithm, the first step is initialization. In fact, first 3 steps are initialization step. That is step number 1, for each vertex U which belongs to the set of vertices capital V, the key value of the vertex is initialized infinite. Initially it is initialized infinite and its parent is initialized null, assuming that it do not have any parent. Then as we proceed further, then accordingly parents is decided, and the parent in case of minimum spanning tree is the one from where the minimum cost edge is possible. As I told, R is the root or the node from where we start to create the spanning tree. So we initialize its key value as 0 because there is no cost involved to reach on that particular node. So we are at that particular node only, so its value will be 0. And another variable NSV, that is also known as set of fringe vertices, it initially consists of all the vertices which are possible available into the graph. If graph have say 5 vertices, so NSV will be having those 5 vertices, say A, B, C, D and E. Then what we do, we retrieve the vertices from the fringe set of fringe vertices one by one till there is no vertices left into the set of fringe vertices. And once we retrieve, initially we retrieve the root and thereafter we retrieve the next node based on the weight factor. So that is, if we retrieve say U, extract the node with minimum key value in NSV. So from fringe node or the node which is not already included into the minimum spanning tree, we select a vertex and we remove that vertex from the set of unvisited vertices, and then we check the cost of that vertex. So for each vertex V which is adjacent to that particular node U, if V belongs to NSV and weight from U to V is less than the weight of that V, then we modify the weight. That is, if the weight is say from parent A, the weight of a node B is 10 and from another node the weight is say 4, then we will modify the weight as 4 because it is lesser, and accordingly we modify the parents also. So in that case V's parent will be the U and the new value of V will be the weight from vertex U to V. This will be more clear when we discuss the example. Let me take this particular example to explain the working of Prim's algorithm. So as I told that first 3 steps are the initialization step. So here in this graph we can see that there are 7 vertices, namely A, B, C, D, E, F and G, which is represented in the first column of the table. And then we initialize the parent for every node, every vertex. So we want to start from the vertex A, and so A will be a root node and its value will be 0, initialized as 0, and for remaining of the vertices say B, C, D, E, its parent will be initialized as null. We assume that which will be parent, that will be decided later on. Initially we initialize it null as per the algorithm, and their weight from A is initialized as infinite in beginning. So this is the initialization in case of Prim's algorithm for this particular graph. Thereafter we select the first node, that is A. So A is selected, it becomes the root and its value is 0. Then we see in the graph which other nodes are reachable from A. So in this particular graph we can see that from A it's a C which is reachable, and as well as vertex B is reachable. So in the previous slide we can see that the value of B and C was initialized infinite, but now because the weight from A to C and A to B is lesser than the infinite, so that infinite value is modified equal to that actual weight of the path from A to B and A to C. So for B its parent will become now A because it is reachable from A, and for C also the parent will be A, and its weight or key value will be 2 and 1 respectively for B and C. Thereafter, we select the remaining out of remaining vertices, we select the one whose weight or key value is minimum. So in this table we can see that the key value minimum is of node C or vertex C. So we select C and we form a tree from A to C, like here in this slide. We can see that we have considered the edge from A to C into the MST, and thereafter we see from C, vertex C, which other vertices are reachable. So we find that from C, its vertex D and vertex F are reachable. So now we modify the weight or key value of vertex D and F from infinite to 7 and 6 respectively, and accordingly we change their parents from null to C, because these two nodes are reachable from C. So C will be parent, and the weight from C to F and C to D will be 6 and 7 respectively. So after doing that change, we can see which is there in this slide. Now out of this table we can see which node should be selected next to be included into the minimum spanning tree out of unvisited nodes. So now we have A and C already visited, we have B, D, E, F and G unvisited, and out of these 5, the B is the vertex which is having minimum cost or minimum weight, that is 2. So we will select next 2 as the cost value, and B will be included, vertex B will be included into the MST. So now we can see that A to B edge is connected, A to C it was already connected, and when we reach to the node V, we can see that from B we can directly reach to E and we can directly reach to D. So in the previous slide, when the C was the parent for D, the key value or path value was 7. But when now B is considered as parent for D, its cost value is 4, which is lesser than 7. So accordingly, it is modified in this table from 7 to 4. And now the parent is also modified. Earlier it was C, now it is B, because it is least cost is from B to D. Similarly, from B to E, now we have a path having weight 3. So it is also modified from infinite to 3. So out of these, we can see that now the next node to be selected is that of E, because its cost is minimum, that is 3. So E will be selected and that will be included into the minimum spanning tree. So now we can see that in MST we have an edge from B to E, and from E the direct reachable vertices are B and D, but B is already visited, so we will not touch that, and we will consider D, but the cost to reach from E to D is 5, but from B to D it is 4, so there will be no changes as per the Prim's algorithm. So after selecting E, we have the unvisited nodes D, F and G, and then we look whose cost is minimum out of these D, F and G. So it is D which is minimum. Its cost is, its weight is 4 to reach from B to D. So we will include that D into the MST. We can see that here the D is included into the MST, and now we have only 2 fringe nodes or fringe vertices, F and G only. So once we included D, then there is a direct path from D to F and D to G, but the cost of D to F is 9, whereas the cost to reach F from C is 6, so there will be no change in that case. And the cost to reach from D to G is 2, and earlier it was infinite, so it will be modified 2. So out of the unvisited node F and G, now the minimum cost is 2, so G will be selected and it will be included into the minimum spanning tree. And from G to F there is a path, but its cost is 8, whereas the path from C to F is having cost 6, so it will not be modified. And finally we will insert an edge from C to F. So this way the Prim's algorithm works, and this is the minimum spanning tree. So here in this slide we can see that the cost of the minimum spanning tree is 1 plus 2 plus 3 plus 4 plus 2 plus 6, that is 3, 3, 6, 10, 16 or total 18. So 18 is the total cost, total weight of the minimum spanning tree. As per the other properties of spanning tree, we can see that all the 7 vertices are included into the minimum spanning tree. Also, the number of edges are 1 less than the number of vertices. That is, there are total 6 edges in the minimum spanning tree. And it also do not contain a cycle because it is a tree. So that is how we can use Prim's algorithm to construct a minimum spanning tree for a graph, weighted graph. Now the question comes, what is the time complexity? How much time it will take to create a minimum spanning tree for a given graph? So as in algorithm, we can see that there are two parts. One is the loop where we are creating the MST, another is the initialization part. So the initialization steps are completed in order of mod V steps, where V is the number of vertices, while the loop execute until all nodes are traversed, or it will be executed mod of V times. If it have 10 vertices, so outer loop will be executed 10 times. And while executing the outer loop, every time a node will be extracted, and extraction will be performed using a heap. So in the heap, if you are aware that it requires order of log V times. So thus there are V number of nodes. So each requires order of log V. So total time will be V into log of V. Similarly, the number of adjacent edges can maximum be 2 mod E. The for loop will require order of E, and as heap is used, overall it will require order of E into log of mod V time complexity. So total time complexity will be sum of all these time complexity, because in time complexity we consider the higher order of the polynomial. So finally the time complexity will be order of mod E log V. So this is how we can analyze this algorithm. Then the next question comes that what are the advantage of Prim's algorithm? As I told that for minimum spanning tree there are one more algorithm, popular algorithm, that is known as Kruskal algorithm, but we are not going to discuss about that as of today. We will cover that part into any other lecture. So in comparison to that Kruskal algorithm, in fact Prim's algorithm is guaranteed. Even both algorithms are guaranteed to find the MST in a connected weighted graph. So is the case with Prim's algorithm. If there is a connected weighted graph, then this algorithm gives guarantee to find the MST, one of the MST, because in sometimes there may be more than one MST is possible. Also its time complexity, as we have seen that order of E log V using binary heap or Fibonacci heap, where E is the number of edges and V is the number of vertices. And this algorithm is a relatively simple algorithm to understand and implement as compared to the other algorithm or Kruskal algorithm. We will discuss that into the next lecture. But there are certain disadvantages for Prim's algorithm. So what are those disadvantages? Prim's algorithm can be slow in case of dense graph is there, dense graph or nearly completed graph, as it will require iterating over all the edges at least once. So it may consume more time. Prim's algorithm relies on a priority queue which can take up extra memory and slow down the algorithm on very large graphs. This is the another advantage. And the choice of starting node, as in our example we have chosen say vertex A as the starting vertex for constructing the MST. One can select any other vertex as a starting one. So the choice of a starting node can affect the MST output, which may not be desirable in some applications. So these are few of the disadvantages of MST, Prim's algorithm to construct the MST. Then there are certain applications of minimum cost spanning tree, like one of the most important application is traveling salesman problem. Another application is in electronic circuit design to connect say n pins by using n-1 wires using least wire. For that we can use Prim's algorithm. Spanning tree also finds their application in obtaining independent set of circuits equation for an electrical network. So in summary, we have today discussed minimum spanning tree that have the minimum weight among all the possible in spanning tree. We have discussed about Prim's algorithm. We have discussed about the time complexity of the Prim's algorithm, and we have discussed the applications of the spanning tree. Thank you.